All right, let's go ahead and get started with lesson 6 on covalent bonding. This lesson will discuss the third and final bonding type in this unit. This will be the part 1 of 2 for this lesson 6. All right, so let's get into the definition of covalent bond. A covalent bond is formed by the electrostatic or Coulombic attractions between a shared pair of electrons and the positively charged nuclei. Covalent bonds usually occur between nonmetal atoms that share their valence electrons to complete their outer shells, or to form that stable octet that we've referred to in previous lessons, forming both molecules or polyatomic ions. We can model covalent bonding through these two models or drawings here. So in the first one, we have a representation of two nuclei. Here's 1 and 2, and of course both of those nuclei are positive because of the protons there. Now, both of these nuclei are attracted to a pair of electrons, which is represented by here. Now that attraction between the nuclei and the two electrons is a Coulombic or an electrostatic attraction, obeying Coulombic's laws, and that attraction forms a covalent bond. Now every covalent bond is a sharing of two electrons between two nuclei of different atoms, which is totally represented by this model. Now there's some forces here that exist in order to create a perfect covalent bond. We have some repulsion forces and attractive forces. Now, of course, the attractive forces are between the nuclei and the two electrons that are being shared. Now, these attractions are indeed electrostatic attractions that obey Coulomb's law. So the closer the electron is to the nuclei, the stronger the attraction, and the further away they are, the weaker the attraction. Also, the stronger the nuclear charge in the nuclei, or in a particular nucleus, the stronger the attraction on the electron, following Coulomb's principles here. But we also have some repulsions that occur. Now, these repulsions are going to be between the electrons that are being bonded. And you can think this is pretty obvious, and we've talked about this before. When electrons are too close to each other, too cramped, they repel each other. And they repel each other in the same principles that Coulomb law applies to. The closer those electrons are to each other, the larger the repulsion. That's true, all right? Now, what about the repulsion between the two nuclei? Well, those nucleuses are very positive. And if they get too close to each other, of course they're going to repel from each other because they obey Coulomb's law. The closer those nuclei, the stronger the repulsion between the nucleuses that we see here. All right. Now, in order to create that covalent bond, though, between these bonding electrons that are being shared and the two nuclei, these forces, repulsion and attractive forces, have to balance one another. There has to be a nice balancing act in order to create a perfect covalent bond. Now, the other thing I want to point out that we look in the second picture over here is that when we form a covalent bond, there is an overlapping of the valence shell between both atoms. And that's important to understand, the overlapping of the valence shell between these two atoms. And you can see this overlapping that occurs right here. And you can see the two electrons that are being shared between those two nuclei. The two nuclei, the attraction of those shared electrons. Now, in most cases, not all, but in most cases, each electron that is being shared is donated by each atom. So one atom donates one of the electrons, and the other atom donates the other one, and then they share both electrons after that. All right? But to share, by the way, again, to reinforce that, in order to share those electrons, we must have a balance of the attraction and repulsion forces, but we also must have an overlap of the valence shells. All right, so here we have kind of a model of hydrogen. Hydrogen being a nonmetal, it can form a covalent bond with itself. So if we take two hydrogen atoms, remember that hydrogen has a nuclear charge of +1, has one proton, and it also has one electron. So when we take two hydrogen atoms and we're going to form a covalent bond between them, there is an overlap of the valence shell, and there's a sharing of the two electrons between the nuclei of both hydrogen atoms. There's the attraction. All right? And again, in this case, we can see that each atom is donating one of the electrons that are being shared in the covalent bond. And then one last time, just want to reiterate that every covalent bond, there is two electrons being shared, and that's important to remember. All right? Now, a little bit more detail on the balancing act between the attractive and repulsion forces here. Now, this graph is an important graph to make note of and to understand. And so we're going to kind of talk ourselves through this at all. Now, we mentioned earlier then, in order to form a perfect, stable covalent bond, is that we have to have the right balance of attraction and repulsion forces. And when we do that, it creates a minimal potential energy between those two atoms. And remember that all atoms want to form chemical bonds that not only complete their octet, give them a full valence shell, but minimizes their potential energy, get them as low as they possibly can. And so at the point, as you can see on this graph here, the perfect covalent bond situation for these two atoms is at a minimal potential energy of negative 436 kilojoules per mole. That gives us a minimal low, and at that point, both the repulsion and attractive forces in that covalent bond are perfectly balanced, creating that minimal potential energy low. All right? Now, let's draw a couple of things here. I'm going to erase this, and let's start up here. Now, we're going to look at a couple of atoms here, and the potential energy is on this y-axis, and the distance or the radius between the two atoms, or specifically between the two nuclei, represent along the x-axis. Okay, so when you have two atoms that have a radius in this area here, the potential energy is too high. There's not a good balancing act to form a strong covalent bond. So up here, the radius is the two atoms are far apart. They need to get closer together. And so what's going to happen is around here, the radius is smaller, the atoms are closer, and you can see that the potential energy is starting to dip the closer these atoms get. And finally, it dips to the minimal point where the distance between the two nuclei are perfect. It's the most stable distance between the two nuclei to form the best covalent bond. But if the nuclei get too close to each other, then there's a quick jump in potential energy. So in other words, what we're saying is if the nuclei are too far apart, it doesn't form a very good stable covalent bond, and the potential energy is still too high. And so the radius, as the radius shrinks, so these two atoms get closer and closer together, then the potential energy goes down, and we're beginning to form a better covalent bond, more stable, until we get to the minimal amount of energy, which is recognized here. So the distance, or the radii, that's perfect between these two nuclei to give us the best covalent bond is about 74 picometers, and then gives us the negative 34 kilojoules of energy at the minimal. But if that distance gets smaller, so say it gets 76 picometers, those two nuclei are way too close, and therefore now the repulsion forces between the nuclei increase so dramatically big that the potential energy goes way up and the covalent bond becomes unstable. So bottom line is the covalent bond, the perfect covalent bond, is stabilized when the attractive, let me erase that, when the attraction and repulsion forces are perfectly balanced between them. Now, this length, the radius between those two atoms that form that perfect balance of force, is known as the bond length. All right. Now, the bond length is a definition that you need to know and have down in your notes. Essentially, the bond length occurs at the minimal potential energy where the attraction and repulsion forces are balanced. And that is the definition of bond length. Again, the bond length gives us the best possible covalent bond between the two nuclei. It gives us the perfect balancing between the attractive and repulsive forces. All right, so I hope this is clear. I hope this is helpful. If you need to relook at this lecture video, do so. Again, this is just part 1 of 2, and so this is it for part 1. And then make sure that you study and prepare for the quiz on this, and then watch the lecture video on part 2. And that is it for now.